Dear students, this is our 29th lecture on bioorganic chemistry, and today we will discuss about calixarenes. The calixarenes they were named as by Gaucher to specify the shape of the phenol-derived cyclic tetamer in conformation in which all the four aryl groups they are oriented in the same direction, and these calixarenes they are so called as model of these. They resemble a Greek ancient Greek vase called Calixar crater, and you can see over here that these are designed in such a way that the OH groups present, the four OH groups present, they form the endorim of the vase, lower rim of the vase, whereas these para-substituent aryl groups they are pointed upwards, they are exorim of the vase. So their orientation in case of calixarenes is very important, and these calixarenes they have these aromatic rings, they are bound in such a manner that they form the exorim, whereas these hydroxyls they form the endorim of these molecules. And the common system of nomenclature of these compounds is that their name starts with prefix calix, and this calix is followed by the number of phenol moieties which are linked by the methylene in square brackets. So for example, we will, if there are say 4 phenol groups, we say calix 4 arene, and the kind of substituents present they will be added before the name calix in the ring. For example, in this case, if this R is tertiary butyl group, then that means tertiary butyl group is present at position 5, 11, 17 and 23, whereas these hydroxyl groups of phenols they are present on carbon number 25, 26, 27 and 28. So that therefore name will be 5, 11, 17, 23 tetra tertiary butyl. So these are 5, 11, 17, 23, where R is tertiary butyl. So tetra tertiary butyl, then calix 4 because 4 phenol moieties are there, and the position of these hydroxyl groups is 25, 26, 27 and 28. 25, 26, 27, 28 tetraol, that will be the name of this calixarene in terms of systematic nomenclature. So similarly we can name different types of calixarenes. For example, this is the basic calix 4 arene, where 4 phenol moieties they condense with 4 molecules of formaldehyde to give us this type of calixarene, and this is calix 4 arene 25, 26, 27, 28 tetraol. Similarly, this is formed by combination of 8 phenolic moieties, 1, 2, 3, 4, 5, 6, 7, 8 phenolic moieties joined by methylene group. So calix 8 arene and then the position at which the hydroxyl groups are present: 49, 50, 51, 52, 53, 54, 55, 56. So depending upon the number at which the hydroxyl group is present, we will name them accordingly. Then similarly, this is CLEX 6 arene, this is again CLEX 4 arene, where 2,3-dibromo-3 oxo calixarene is the derivative from which they have been formed. Then is Calix 4 arenes. They can have these 4 conformations in which they can different groups can be present, and these conformations, basic conformation is the cone conformation, where all the 4 hydroxyl groups are present on one side and all the 4 aromatic rings, they are present on other side of the molecule. Then partial cone is where 3 hydroxyl groups and 3 aromatic rings, they are on the same side, whereas one aromatic ring is present on the side of hydroxyl group and one hydroxyl group is present on the side of the aromatic ring. This is called as partial cone. Then 1,3 alternate is that 1 and 3 alternatively they are present. In one case both the R and at 1,3 position both the OH, they are on the same side. So this is 1,3 alternate. Similarly, we can have 1,2 alternate, where both the hydroxyl groups and the aromatic rings, they are present on the same side and they are on the opposite side alternatively. So this is 1,2 alternate or 1,3 alternate conformations of calixarenes. And the parent calixarene, CLEX 4 arenes and CLEX 5 arenes, they exhibit only the first one, that is cone conformation. But if we increase the temperature at elevated temperature, and they undergo ring inversions between 2 cones. Then synthesis is that they are easily available, as they can be synthesized using inexpensive materials through one pot reaction. So basically we have to condense the phenols with formaldehyde to give us different types of calixarenes in the presence of a base. So here we can have CLEX 4 arenes if N is 4, 5 if N is 5, CLEX 5 arenes, 6 arenes, 7 arene or 8 arenes, depending upon the number of formaldehyde units which condense with the phenolic moiety. The applications of these calixarenes, they are enormous. First is that they can make a complex with aromatic guest atoms, and these complexes, they may be 1:1 or 1:2 complexes which can be formed with the aromatic gas. 1:1 complexes, they are also called as endocomplexes, and here the aromatic guest enters the cup-like cavity of the calixarenes, whereas in 1:2 complexes, 2 calixarene units, they form a capsule where the aromatic compound is hosted as a guest. Then calixarene 6 and 8, they do not form endocomplexes, so they will only form 1:2 complexes. whereas CLEX 5 arenes they form these 1s-to-1 or endocomplexes. Then these calixarene derivatives they can undergo complexation with neutral molecules or ions also. So for example, this highly water soluble sulfonated calixarenes where this is sodium sulfonate group present which makes it soluble in water because of the presence of this sodium salt. So this has increased ability to host neutral molecules or ions in its cavity. Then if we add this group at the tether of the lower rim of the compound, then this gives a 1s-to-2 complex with fullerene in water, exhibiting the strong electronic interaction of charge transfer type between host and the guest molecule. So here the complexation becomes very strong because of the formation of a 1,2 fullerene complex. Then calixarenes they can also undergo complexation with crown ethers. So for example, calixarenes they can combine with these types of crown ethers to have a stable complexes which can be used to detect uranium in different types of compounds or nuclear ways. So they can complex with anions as well as cations based on the presence of these hydroxyl groups or hydroxyl groups in calixarenes and these oxygen atoms in case of crown ethers. Then this is another type of calixarene crown ether complex which can be used for complexation with anions and cations. Then this is another type of host which is developed by combination of these calixarenes and these 2,4-diaminotriazine moieties. So because of the formation of hydrogen bonding, this can be used for the selective binding to the barbiturates. So they can be selectively bound to these types of receptor molecules. And then these calixarenes they can also undergo complexation with the metal ions. Different types of metal ions depending upon the selectivity can be complexed with these types of calixarenes. For example, this tetra-O-methylated, so the 4 hydroxyl groups they are methylated to give us tetra-O-methyl calixarene derivatives, and these derivatives they can selectively bind lithium or sodium or ammonium derivatives in different parts of the system. For example, if we are having lithium or sodium, this will bind to the O-methylated part of the ring, whereas if we are to bind these ammonium derivatives, then they will form a cone ammonium complex in the aromatic region of the calixarene. Then calixarenes they can be used for separation of different types of ions and one of the most important approach is the use of these CLEX 4 arene and crown ether compounds absorbed on silica gel to provide a column which can be capable for separating cesium ions and potassium ions from alkali metal ions. So this is one important application where we can separate cesium ions and potassium ions from alkali metal ions. Then para-tertiary-butylcalix 8 arenes, they have been used for recovery of cesium from nuclear waste. And then another example, para-tertiary-butylcalix 4 arenes and substituted tertiary-butylcalix 6 8 arenes. They are used for the separation of actinides from lanthanides in radioactive waste. So different types of arenes, they have different application for separation of ions. Similarly, a hazardous mercury has also been separated from the waste by mercaptocalix 4 arenes of this type, where any of these substituent is a thiol moiety SH. So either this Z1 is SH, all other they are hydroxyl groups, or Z3 is SH, or others Z1 and Z3 they are SH, and these two they are OH, or all the four they can be replaced by SH. So depending upon the type of environmental waste from which the mercury is to be separated, we can use different types of complexing agents for separation of mercury from the environmental waste. And it has been seen that these types of calixarenes, they show selectivity for Hg2 plus ions over cadmium or lead2 plus ions. Then some molecules, they can also be separated by these calixarenes. For this, the concept of perforated monolayers has been used for the permeation selectivity of gases, which bind through complexation with the calixarenes. For example, this poly 1-trimethylsilyl 1-propyne derivative, this is used as the porous membrane on which this calixarene is deposited, and then these monolayers which are prepared by combination of this porous membrane with the calixarene, they showed varying degree of permeation towards pair of gases such as helium and nitrogen, or helium or antimony hexafluoride. So these can be selectively permeated on these porous monolayers which are formed from the reaction of this with the calixarenes. Then calixarenes, they can also be used as ion or molecular selective electrodes. For example, electrode selective for H ions, we know from many years. Then the important selective electrodes, they are for blood sampling, for example. So first calixarene-based ion selective electrode was used for detecting these sodium plus ions. For example, the calixarene based on these tetra-esters, where Z is some ester, this is particularly effective for selective detection of sodium plus ions. Then these calixarenes, they can be used as chromogenic and fluorescent sensors. So we know that the substances which change color or change fluorescence in response to change in their environment, they are very important for humans since ancient times, and we have used calixarene-based systems as sensors for such type of chromogenic and fluorescent applications. For example, this calixarenes, which is based on this indo-aniline moiety, is used for the separation of calcium 2+ ions, because calcium 2+ ions, they show a bathochromic shift on complexation with these types of calixarenes. Another simple calixarene is para-sulfonato-calix-4-arene, which forms a colored complex with cesium 3+, and therefore this can be selectively used for cesium 3+ ion among the rare earth metals. Then this is para-nitrophenylizo-based calixarenes. These have been selectively used for complexation with lithium ions or sodium or potassium ions, depending upon the substitution present at these Z1, Z2 or Z3. And it has been shown that the calixarene where Z1 and Z3 is equal to this type of ether, and Z2 is ethyl, that shows a selectivity towards sodium to potassium which is more than 1260 times better in terms of sodium selectivity. So like this we can have different types of chromogenic and fluorescent sensors, where by changing this substitution of different groups at Z1, Z2 and Z3 position. But this part, para-nitrophenyl isochromophore, has to be the same. Then another compound which is capable of discriminating between enantiomers of 1-phenylethylamine and norepinephrine, and that is based on fluorescence quenching, that is chiral CLEX-4 which carry S conformation of di-2-naphthyl prolinol moieties on the lower rim of the calixarene. Then we can make a sensor for these types of acetylcholine, which is a neurotransmitter. So this can displace polycyclic substituted pyridine ion, and this type of pyridine ions, polycyclic substituted pyridine ions from its complex. And the calixarene which has been used is para-sulfonato-calix. 6 arenes are used for these sensor applications. Then nonlinear optical compounds having these types of nitro moieties, they have been used for nonlinear optical behavior of different types of compounds. And calixarenes, they have been used for these applications like frequency doubling of laser light, electro-optical switching devices, and optical communication phenomenon. And in most of the cases, CLEX-4 arenes carrying these nitro moieties, they have been used for these types of nonlinear optical behavior of compounds. Then calixarenes, they have also been used as biomimetic catalysts. The biomimetic reaction, for example, in case of hydration of 1-benzyl 1,4-dihydronicotinamide. So this is 1-benzyl 1,4 dihydronicotinamide, and this reaction is catalyzed by para-sulfonato-calix 6-arene. So this is a biomimetic catalyst in place of enzyme glyceraldehyde phosphate dehydrogenase. So this reaction where in presence of H ions, this gets converted into this quaternary ammonium salt, and this on hydrolysis produces this hydroxy compound. So here this calixarene is used as a biomimetic hydration reaction of these types of nicotinamide reaction, which is in substitution to enzyme activity of glyceraldehyde phosphate dehydrogenase. Then calixarenes they are also used as photoresponsive molecules, and they are capable of reversibly switching between two distinct states of currently receiving considerable attention. So now the calixarenes they are being used as optical data storage systems. For example, calixarenes carrying these types of anthracene moiety on the lower rim of the molecule, they undergo intramolecular ring formation at these two places to form these types of compounds. So these double bonds present at the anthracene, they form one bond is formed, carbon-carbon bond is formed at this place, and one carbon-carbon bond is formed at this place, whereby this compound calixarene A is converted into calixarene B, and this when calixarene B is irradiated with 350 nanometer light, then it undergoes intramolecular ring formation to B. So when A at 350 nanometers is irradiated with UV light, this will get converted into B, and if it is irradiated with UV light at 280 nanometers, then B will be converted back into A. So this is how they can act as photoresponsive molecules, and it has been shown that B has a considerable higher affinity for sodium ions than in comparison to A. Then calix-4 arenes which contain these types of azobenzene moiety in the lower rim, they can also undergo syn-anti interconversions when they are irradiated with UV light, and anti-isomer has been found to show higher bending capacity for these types of cation, sodium or potassium, nickel, copper, zinc, cadmium or aluminum in comparison to its syn isomers. Thank you very much.